Hello and welcome to online lecture number 12 for Chemistry 112 during the spring semester of 2020. We are still in chapter 17, and this is the last of the lessons concerning balancing redox reactions. In this lesson, we're going to introduce a different method called the oxidation number change method. When we say oxidation number change, this refers to, as the name implies, the difference in oxidation number of an element as part of a reactant compared to its oxidation number as part of a product. So it's for a reduced element or an oxidized element, it's how its oxidation number has changed. And the idea, as we'll see as we get into this lesson, behind this oxidation number change method to balance redox reactions is we determine the oxidation numbers of all the elements, we determine what's been oxidized, what's been reduced, and one of our main, very early on goals is to ensure that the total increase of the oxidation number of the oxidized element is the same as the total decrease in oxidation number of the reduced element. And as we did before we get into more complicated examples, we'll go over a couple of very simple examples just to get used to this new way of thinking about oxidation number changes and how that helps us balance a redox reaction, as we'll see, very efficiently, very fast. So our first example was copper 2 plus aluminum produces aluminum 3 plus copper. And we're just going to, in this example, just going to determine what the oxidation number change is for the oxidized element as well as the reduced element. So we have our reaction. And as we did with the half reaction method, all the times we start with just simply determining what are the oxidation numbers of all the elements in the reactant side as well as product side. So as we did before, this is going to be positive 2, 0, positive 3, and 0. And that's going to be key for this method is for us to be able to determine these oxidation numbers very accurately. And in order for this to be an efficient method, we also need to be able to determine oxidation numbers relatively efficiently. So we have our two elements, one substance is oxidized, one substance is reduced. And we'll determine that difference in oxidation numbers. So we have copper and aluminum are the two chemical species that are either oxidized or reduced, either losing electrons or gaining electrons. Copper, on the reactant side, has a positive 2 oxidation number. On the product side, it has a 0 oxidation number. So the difference is -2. In other words, copper has oxidation numbers gone down by 2, therefore it must have gained electrons, specifically gained 2 electrons. Aluminum went from 0 to positive 3, so its oxidation number increased, it's oxidized, it's increased by positive 3. So these are the oxidation number differences of the reduced substance, reduced element, and the oxidized element. And the goal here, as we'll see with this method, is to very early on start by changing these respective coefficients to ensure that this number in magnitude is the same as this number in magnitude. There will always be opposite signs. We want to make sure that the decrease here is equal to, but opposite sign, of course, of the increase here. So that's for our first example. And then in our second example, we're going to do the same thing. Just simply at this point, get used to determining what those changes are in the oxidation number of the reduced element as well as the oxidized element. So we have our silver plus copper produces elemental silver and copper 2 plus ions. Determine oxidation numbers of everything. Silver is a monatomic ion, so that's going to be positive 1, same as the charge. Copper is an element, so it's 0. Silver is an element, 0. And then copper 2 plus, another monatomic ion, so that's going to be positive 2. So once again, with our silver and copper, which are our two species that are being either oxidized or reduced, we have silver goes from positive 1 to 0. So its oxidation number decreased by 1, it's been reduced. And copper goes from 0 to positive 2. Its oxidation number increased, it's been oxidized by a difference of 2. So these are our differences in oxidation number as written. In the end, we want to make sure that this number is the same as this number, but of course opposite in sign. So with those two quick examples, just introducing what we're going to start with, or very early on start with balancing equations. And this is really the hardest part of this whole process, is determining the oxidation numbers and then figuring out what to do to ensure that this number is the same as this number. And as we did for the half reaction method, we're going to do the same thing for the oxidation number change method, in that we're going to introduce the series of steps that we need to follow, the systematic method to follow to balance these reactions according to this method by illustrating these rules, these steps, with a very simple example, with that example that we left with on the last slide. So the first step is to mass balance every atom except for hydrogen and oxygen. And as we go through these steps, we want to keep in mind, as we go through steps, we're going to apply these steps to the overall equation. We're not going to worry about breaking up the overall equation to half reactions and then recombine them like we had to do for the half reaction method. These all apply to the overall reaction. So that makes it, in some cases, a little bit simpler and also a lot faster, as we'll see. So we mass balance everything except for hydrogen and oxygen. So with our given reaction, that's already been done for us because we have one silver, balances one silver, one copper, balances with one copper. The next step, as we practiced in the previous slide, is to determine the total change in oxidation number of the oxidized element, as well as determine the total change in oxidation number of the reduced element. And as we illustrated in the previous slide, we've already done that. +1 to 0 for a -1 total change for the silver, what's been reduced, and a +2 total change in oxidation number for copper, the substance has been oxidized. And then here's actually where we start trying to balance this redox reaction. The idea is we want to make sure that those two numbers, those two changes, are the same, opposite in sign, but same in magnitude. In other words, the total increase in what the oxidation number what's been oxidized equals the total decrease in the oxidation number what's been reduced. So in order to do that, we'll look at our differences, as we'll see, and then we'll multiply, we'll use those differences, and we'll multiply our respective coefficients by a factor or factors such that those two numbers are equal in magnitude, but opposite in sign. So we go back to our examples. We have a -1 and +2. So the lowest common multiple of 1 and 2, I'm ignoring the sign, is 2. So I have to think about how can I change this from a magnitude of 1 to a magnitude of 2? Well, I can do that obviously by simply multiplying by 2. So whatever factor I had to multiply this difference by, so that it's the same as this difference, in this case 2, I'm going to do the same thing to all of my compounds or elements or ions that also have this reduced element silver. So in my balance equation, this tells me I need to make this a 2, and I need to make this a 2. Notice that by doing the same thing to the reactant side and product side, I haven't changed any mass balancing that I've already have established. And because I didn't have to change anything with copper, I don't have to change anything with copper. In our next step, we're then going to balance the charge, because as a redox reaction will be balanced, it has to be balanced both by mass and by charge. So we're going to balance the charge by adding hydrogen ions. So this is one difference from the oxidation number change method versus the half reaction method. In the oxidation number change method, we're balancing charge by adding hydrogen ions, not electrons, as we had to do for the other method. So when add hydrogen ions, mature, the total charge on the reactant side equals the total charge on the product side. So when we look at those charges, we have a total of 2 times +1 plus 0, or +2 on the reactant side, which matches the 1 times +2 or +2 on the product side. So as a result, it's already charge balanced. There's no need to add hydrogen ions either to the product side nor the reactant side. And then step 5, we then mass balance the hydrogen by adding water molecules to one side or the other. And as a valid check to make sure we've done everything up to this point correct, when we mass balance the hydrogens by adding water, we should also automatically be mass balancing the oxygens. So we're mass balance the hydrogens, and then once we've done that, then the oxygen should automatically be also mass balanced. If not, that means we've made some sort of mistake up until this point. So I have 0 hydrogens on the reactant side, which matches 0 hydrogens on the product side. So likewise, there's nothing to do here as well. And then finally, it's a good idea to check that what I have now come to is a balanced redox reaction. So it's balanced both by mass as well as by charge. So balanced both by mass and by charge. We've already proven that it's balanced by charge. By mass, we have 2 silver, which matches 2 silver. And we have 1 copper on the reactant side, which matches 1 copper on the product side. So as a result, I now have a balanced reaction. Move these oxidation numbers to eliminate confusion. Now I have a balanced reaction that describes the reaction of silver ions with copper to produce silver and copper ions. So it's a very simple example, but as we said, the main idea here is just to illustrate the examples of how to use those various steps of this oxidation number method. Then we'll continue on going actually through the same examples, same redox reactions that we did for the half reaction method, so that you as the student can compare the two methods and see which method you prefer over the other. We have this example again, where we want to follow this time the oxidation number change method to balance it, assuming that the reaction is taking place in an acidic solution. So our first step is to mass balance in the overall reaction, mass balance everything except for hydrogen and oxygen. So we have one manganese, one sulfur. So that's already been done for us. The next step is to determine the oxidation number changes of what's been oxidized and what's been reduced. In order to do that, we need to determine what the oxidation numbers are of everything in the reactant side as well as what's in the product side. So as we saw in the previous lesson, manganese here is +7, manganese here is a +6, sulfur in the sulfite ion is a +4, and it's +6 as part of sulfate. So the manganese and sulfur, those are the elements whose oxidation numbers are changing. Manganese goes from an oxidation number of +7 to +6. Its difference is -1. Manganese is being reduced. Sulfur goes from +4 to +6. Its oxidation number is increasing. It's being oxidized because it's increased by 2. So we have -1, +2. Now our next step is to figure out what factors do I need to multiply these numbers by in order to ensure that the magnitude of this number is the same as the magnitude of this number. So we get 1 and 2 like we did before. So the lowest common multiple of 1 and 2 is 2. So I can ensure that these two numbers are the same, opposite sign, but otherwise same magnitude, by multiplying this number by 2. That will give me -2, which matches the +2. So because I had to multiply this number by 2, I also want to multiply all my manganese-containing compounds also by 2, their coefficients by 2. So then in my balanced equation, I now have 2 MnO4 minus and 2 MnO4 2 minus. The next step is I then want to balance the total charge by using hydrogen ions. So let's eliminate these oxidation numbers to avoid confusion. All these numbers up here. The charge, we have -2 plus a -2. We have total right now a -4 charge on the reactant side. On the product side, I have -4 plus a -2, or a -6. Notice to balance the charge in this method, I'm adding hydrogen ions, H+ ions. So as a result, all I can do is add hydrogen ions to one side or the other to increase the overall charge, to make a charge less negative or more positive. So I can add 2 hydrogen ions to this side, in other words. And when I do so, then this overall -6 total charge becomes an overall -4. So therefore, the charges are balanced. The next step is to then balance the hydrogen atoms using water. So I added 2 hydrogen atoms to the product side versus 0 over here. So let's squeeze in another 1 water molecule to balance out the hydrogen atoms. 2 hydrogen atoms equals 2 hydrogen atoms. And if I did everything up to this point correctly, then that should also balance the oxygens. So we have 8 oxygens, plus 1 is 9, plus 3 is 12, which does in fact match. 2 times 4 is 8, plus 4 is 12. So we want to make sure that's the last step. We have a balanced reaction, and we want to make sure it's both charge balance and mass balance. We've already proven it's charge balance. And just to double check, make sure it is in fact still mass balanced. We have manganese, oxygen, sulfur, and hydrogen. We have 2 manganese on both sides. Oxygen we just counted was 8, 9, and 12 versus 12. Sulfur is 1 and 1. And hydrogen is 2 and 2. So the reaction is balanced because now it's both mass balanced and charge balanced. And this overall reaction then should be the exact same balanced reaction we got with the half reaction method in the previous lesson. In this example, we have a tin reacted with nitrate to produce tin 4-oxide and nitrogen dioxide. The first step is to make sure everything is mass balanced except for hydrogen and oxygen. 110 equals 110, one nitrogen balances one nitrogen. The next step is to determine the oxidation numbers of the elements on the reactant side and product side, and to ensure that eventually that the total change in oxidation number of what's been reduced equals the total change in oxidation of what's been oxidized. So we have our tin, which is an element, so its oxidation number is 0. Nitrogen is part of nitrate, has an oxidation number of +5. Tin 4 oxide has an oxidation number of +4, and nitrogen is part of nitrogen dioxide, has an oxidation number of +4 as well. So we have our two elements, tin and nitrogen, and tin goes from 0 to +4. Its oxidation number increased by 4. It's been oxidized. Nitrogen goes from +5 to +4. Its oxidation number decreased by 1. So we say nitrogen's been reduced. So we have two different numbers, +4 and -1. So then our next step is to figure out what do I need to multiply either or both of these numbers by to ensure that the magnitude of the difference, magnitude of the change are the same. So we have 4 and 1, the lowest common multiple of 4 and 1 is 4. So I can make this into a 4 by multiplying this by 4. That'll give me -4, which equals positive, which has the same sign, same number, but opposite sign of +4. So if I multiply this by +4, and multiply my nitrogen also by 4. So then the next step is then change my coefficients that are in front of the respective nitrogen-containing compounds to 4s. Let's get rid of the oxidation numbers. The next step is to balance the charge with hydrogen ions, the total charge with hydrogen ions. So we have currently a total charge of 0 plus -4, or -4 on the reactant side. And on the product side, we have a total charge of 0. So I'm adding hydrogen ions, I'm adding positive charge particles. So all I can do is by adding positive charge particles, I can make the charge more positive or less negative. So in other words, I can't make this 0 into -4, but I can make this -4 into a 0. And I can do so by adding the equivalent number, 4 hydrogen ions, to the reactant side. That'll give me a total charge of 0 on the reactant side, which matches the total charge of 0 on the product side. The next step is then to balance the hydrogen atoms by adding water. As I said before, when we do this, this should also automatically balance the oxygens. So we have hydrogen atoms. We have 4 hydrogen atoms on the reactant side, 0 on the product side. So I need to add 2 water molecules to the product side to ensure I have 4 hydrogen atoms on the product side to match the 4 hydrogen atoms I have on the reactant side. So when I do so, I should also automatically balance the oxygens. To see we've done that, we have 4 times 3 is 12 oxygens. And then we have 2 plus 8 is 10, plus another 2 is 12 oxygens. And finally, check this mass and charge balance. We already seen this charge balance. And then the double check that it's mass balanced. We have 10 nitrogen, oxygen, hydrogen, 110, 110, 4 nitrogens, 4 nitrogens, 12 oxygens, 2 plus 8 plus 2 is 12 oxygens, and finally 4 hydrogens matches 4 hydrogens. So this reaction is balanced because it's both charge balanced and mass balanced. Okay, our last example for using this method to balance redox reactions in acidic solution. We have this example, the same example we saw in the previous lesson. So if you've been following along with the lessons, you already know what the right answer is here. But I just think it's a good idea to take some time, pause the video if you'd like to, and try to balance this equation using this different method. Because ultimately, at the end, you need to personally decide whether you prefer this method versus the other method. So as we go through the process, the first step is to mass balance everything but hydrogen and oxygen. 2 iodines versus 1 iodine. So this is where we actually need to do something here. So we have 2 iodines to match these 2 iodines. 1 chlorine matches 1 chlorine. The next step is to determine how the oxidation number of the reduced element has changed, as well as how the oxidation number of the oxidized element has also changed. So we have, for iodine, it's an element. So as a result, its oxidation number is 0. This is for each iodine atom. Iodine over here, its oxidation number, each iodine atom, there are 2 of them total, each iodine atom is +5. Chlorine goes from a +1 to a -1. So we have our 2 elements, iodine and chlorine, whose oxidation numbers are changing in this process, that are either being oxidized or reduced. For iodine, on the reactant side, its oxidation number is 0. On the product side, though, its oxidation number is +5. And remember, what we're interested in here is a total change in oxidation number. So each iodine atom's oxidation number is changing by +5, but we have 2 of them. So in total, we have 10 as a total oxidation number, +10 as a total oxidation number of the iodine atom. The 2 iodine atoms in total on the product side give us a total difference of +10. In other words, between the 2 iodine atoms, they lost a total of 10 electrons because each iodine atom lost 5 electrons. With chlorine, we have +1 to -1. So our difference here is -2. Next step is to figure out how to ensure that the magnitude of this change is the same as the magnitude of this change. So the lowest common multiple of 10 and 2 is 10. So I can make this into a 10 by multiplying this by 5. -10 then will have the same magnitude as +10. So because I have to multiply this by 5, I need to multiply all my chlorine-containing compound coefficients also by 5. So it becomes 5 OCl minus and 5 Cl minus. Our next step is to figure out the total charges and to balance the total charges using hydrogen ions. So our total charge on the reactant side is 0 plus a -5, or -5. On the product side, it's -2 plus a -5, which is -7. All I'm doing is adding hydrogen ions, so all I can do is make a total charge more positive or less negative. So I can make a -7 to a -5, but I can't make a -5 into a -7. So I can make the -7 to a -5 by adding 2 hydrogen ions, 2 H plus ions on the product side. So now the total charges are the same, -5 and -5. And then I balance the hydrogen atoms by adding water molecules. I have 0 hydrogen atoms currently on the reactant side, 2 on the product side, so I need to add 1 water molecule to balance the hydrogen atoms. And by doing so, I should have also automatically balanced the oxygens. So we have 5 oxygens plus 1 is 6 oxygens. Then we have 2 times 3, which is also 6 oxygens. So now I have my overall balanced redox reaction. Finally, to check to make sure it is balanced. It's already balanced by charge. And then quickly by mass, we have iodine elements, oxygen, chlorine, and hydrogen. Iodine, there's 2 and 2. Oxygen, there are 7 plus 1 is 6, rather, and 6. And then chlorine, we have 5 and 5. And hydrogen, finally, we have 2 and 2. So the reaction is balanced because it's both balanced by charge as well as by mass. So those are just a couple of examples, the same examples we saw with the half reaction method of balancing these redox reactions using this oxidation number method, oxidation number change method. But these are specifically done in acidic solutions. So like we saw with the half reaction method, was that there is one method to follow along if you're balancing redox reaction in an acidic solution, and there's a slightly different method to follow if it's in a basic solution. The same thing is true for the oxidation number change method. So we go through these steps, we'll see they're almost exactly the same as the steps we follow for an acidic solution, with one minor and makes sense difference. So mass balance every atom of hydrogen and oxygen, determine our total change in oxidation numbers, multiply respective coefficients by factors, make sure that ensure that the total change in oxidation number of the oxidized element equals the total change in oxidation number of the reduced element. And then what's different is that normally with an acidic solution, we'd balance charge by adding hydrogen ions, because that makes sense, because in an acidic solution, you have lots of hydrogen ions available to participate as part of the reaction. But in a basic solution, that's not going to be true. In a basic solution, the concentration of hydrogen ions will be relatively low, that's why it's basic, but the concentration of hydroxide ions will be relatively high. So in basic solutions, in step 4, we're going to balance charge by adding hydroxide ions to one side or the other. And then step 5 and 6 are exactly the same. We'll then mass balance the hydrogen atoms and oxygen by adding water molecules to one side or the other, and then finally make sure that it's balanced by mass and charge. So we'll finish up this lesson with 2 examples of balancing these redox reactions in basic solutions using the oxidation number change method. The first step, as always, is to make sure everything's mass balanced except for oxygen and hydrogen. We have 1 chlorine, 1 chlorine, 1 chromium, 1 chromium. The next step is to determine the oxidation numbers of everything on the reactant side, product side, and determine that difference in oxidation number of what's been reduced versus what's been oxidized. So as we go through our reactants and products, Cl as part of ClO, as we saw before, is a positive 1. Chromium is a positive 3. Chromium, the product side, though, is a positive 6. And chloride, of course, is negative 1. So we have our 2 elements, chlorine and chromium. Chlorine goes from a positive 1 to a negative 1. So that difference is negative 2. Chromium goes from positive 3 to positive 6. Its difference is a positive 3. So at this point, we want to decide how can we ensure that this number of magnitudes difference is the same as this number. So the lowest common multiple of 2 and 3 is 6. So I need to actually change both numbers, multiply both element compounds by a different factor. 2 and 3 is 6. So to get this to a 6, I need to multiply this by 3. So therefore, I need to multiply all my chlorine-containing compounds by 3. So this would be this one and this one. And then chromium, this is already positive 3, so this needs to go up, multiply by 2. Positive 3 times 2 is positive 6, which matches negative 2 times 3 is negative 6. So because I multiply this by 2, I need to multiply all my chromium-containing compounds by 2. So this would be 2, and this would be 2. Once we have the total change in oxidation number of the reduced element equaling the total change in oxidation number of the oxidized element, now we want to balance charge, figure out charge, and then balance charge. And this is where it differs from the acidic solution method. So our total charge currently is negative 3 plus a negative 2. So we have negative 5 on the reactant side. We have negative 4 plus a negative 3. So we have a negative 7 on the product side. When basic solutions, I'm adding hydroxide ions. I'm adding negatively charged particles. So this is much more similar to what we're used to at the half reaction method, where we're adding electrons, because both electrons and hydroxide ions are negatively charged. So as a result here, if I'm adding hydroxide ions, all I can do is make a positive total charge less positive, or a negative total charge more negative. So as a result, I can make this negative 5 into a negative 7, but I can't make the negative 7 into a negative 5. So to make the negative 5 into a negative 7, I need to add 2 hydroxide ions. By adding 2 hydroxide ions, I now have a charge balance reaction. Negative 7 equals negative 7. And then finally, to balance the hydrogen atoms, I do so by adding water molecules to one side or the other. So to balance the hydrogen atoms, we have a total of 8 hydrogen atoms plus 2 is 10 versus 0. So that means I need to add 5 water molecules to this side to balance out the hydrogen atoms. And if I've done everything up to this point correctly, I should have also balanced the oxygens. So we have 3 oxygens plus 8 oxygens is 11 oxygens plus 2 oxygens, 13. We have 8 plus 5, which is also 13. So finally, to double check everything, charge is balanced. And then by mass, we have chlorine, oxygen, chromium, and hydrogen. We have 3 chlorines, which matches 3 chlorines. We have 3 oxygens plus 8 oxygens plus 2 oxygens is 13 oxygens, which matches the 13 oxygens we have on the product side. Chromium is 2 and 2. And finally, hydrogen is 10 and 10. 8 plus a 2 is 10, which equals a 10 we have here. So we have a overall reactions balance because it's both mass balanced and charge balanced. And then one more example, and like I said for the previous class example, I encourage you to attempt the same problem, balance this redox reaction in basic solution, using the oxidation number change method. So going through our process, first step is to balance everything by mass except for hydrogen and oxygen. 1 manganese equals 1 manganese. The next step is to determine the oxidation numbers of everything to ensure that eventually the total change in the oxidation number, what's been reduced, equals what's been oxidized. So we have manganese, positive 2, so its oxidation number is positive 2. H2O2, as we saw before, oxygen is negative 1. MnO2, manganese is positive 4, and as part of water, oxygen's oxidation number is minus 2. So we have manganese and we have oxygen. Manganese goes from a positive 2 to a positive 4. Its oxidation number increased by 2. Oxygen goes from a negative 1 to a negative 2. Its oxidation number decreased by 1. So to make sure that these two are the same, I need to multiply the change in oxidation number of the oxygen by 2. So therefore, I need to change the respective relevant oxygen-containing compound, also multiply its coefficient by 2. So when I do that, that'll give me then 2 water molecules on the product side. Next step is determine charges, and to balance the charge, because it's done in a basic solution, balance the charges using hydroxide ions. So currently our total charge we have is positive 2 on the reactant side and 0 on the product side. I need to balance charge by adding hydroxide ions and negatively charged particles, so total charge less positive or more negative. So I can make the positive 2 into a 0, not the other way around. So I can make the positive 2 into a 0. I can do that by adding 2 hydroxide ions. That'll give me a total charge of 0 on both sides. And then to balance, mass balance the hydrogen atoms by adding water molecules. So we have 2 plus 2 is 4 hydrogen atoms, which equals the 4 hydrogen atoms we have on the product side. So the hydrogen atoms are already balanced, mass balanced. So therefore the oxygen atoms should also already be mass balanced. We have 2 oxygens plus 2 oxygens, 4 oxygens. 2 oxygens, 2 oxygens gives us 4 oxygens. So it's charge balanced, and just once again to double check that it's also mass balanced, we have our manganese, hydrogen, and oxygen. We have 1 manganese matches 1 manganese. We have a total of 4 hydrogens matches 4 hydrogens, and we have a total of 2 plus 2 is 4 oxygens, which matches the 2 plus 2, 4 oxygens. So this reaction is correct, as we now determine it's both mass balance and charge balance, so we have an overall a balanced redox reaction. So as I said a couple times before, so go through these 2 videos and just decide for yourself which one you prefer. And this method, as hopefully you've seen, is a lot faster, but it strongly depends upon you being able to determine what these oxidation numbers are of the elements in the reactant side and product side. These numbers have to be accurate. If not, then there's no way they should be able to balance the redox reaction. Whereas in the half reaction method, you can completely not know anything about oxidation numbers and still be able to balance the redox reaction. So that's kind of the trade-off, I think, between these 2 methods. If you're good at oxidation numbers, I would probably suggest this method. If you're not so good at oxidation numbers, then perhaps the half reaction method might be an overall more efficient and maybe even overall more accurate method for you.